Thank you very much, Will, for the introduction and the invitation to speak. Before I get started, let me just give a little perspective on who I am and what I do. I'm a professor at Columbia. I'm basically, my background is not so much, let's say, business or economics, but more engineering and operations research. So I'm really interested in problems around stochastic control, decision-making over time when there's future uncertainty. I'm also interested in the applications of that, and the main applications I focus on are focused around finance, particularly things like quantitative trading, optimal execution, things like that. I'm also a practitioner. I'm a principal at Bourbaki LLC, which is a quantitative investment advisor. And so what I'm going to talk about today is machine learning from the perspective of what is happening on the ground in the world of quantitative investing, from the perspective of both, at least my view of what's going on in industry, from my own experience and from my interaction with others, and at the same time, what is the state of the art in terms of the academic research. So it's going to be a little bit less like some of the talks we saw at the very beginning of the morning, but it's going to be very resonant with the panel that we had earlier. Just to get a few things out of the way in terms of what do I mean by quantitative investing, what I really mean is active asset management. I mean buying or selling because you have a view. You're buying because you think the price is going to go up. You're selling because you think the price is going to go down. And this is the area where I think machine learning is most relevant. What I'm not going to be talking about are things like smart beta or factor investing or investing to earn risk premia or so on. Sometimes these things get identified in the same quantitative world, but I'm not going to speak about that, A, because that's not my expertise and be just speculating, and B, also, I think in the ways I'm going to talk about machine learning here, in terms of true sort of data-driven machine learning, those ideas apply much less in that space. But to get started, I think it's helpful to sort of try and understand the broader trends in data science, artificial intelligence, machine learning that we see not just in finance, but in other areas. And really, in the past 10 years, maybe the past 5 years, there's been tremendous breakthroughs in applying some of these methods in different areas. I think it's helpful before we focus on finance to take a look at some of those ideas and see whether and how they might apply. So I'm gonna start with two things that I think are quite impressive. The first is computer vision, more specifically image recognition. Right? Suppose I want to look at this picture and recognize it as a cat. How do I do that? Right? So, this is a problem that's been studied for 30 or 40 years, basically as long as we've had computers and digital images or so on. But really, in the past, 5 to 10 years, there's been breakthroughs, these ideas of, deep convolutional neural networks and so on. And now we're at the stage where, problems like object recognition, facial recognition, and so on, computers are actually, have superhuman levels of performance. So, there's a lot of innovation there, a lot of kind of engineering know-how. But if we take a step back and think about this for 1 second, recognizing that this is a cat and not, say, a Snapple bottle, this is an easy problem, right? A 2-year-old could do it. You can, in fact, train a dog to do it. Dogs do it naturally. They don't even need to be trained, right? So in some levels, this is obvious. Right? Now, again, I don't want to take away from the innovation of this work. The challenge really is getting a computer to do it. And the main sort of challenge there is lack of representations of, the universe of naturally occurring images. Right? So the problem these deep neural networks are solving is not so much a challenging problem of object recognition. The problem is easy, right? But the problem of coming up with good recognitions, good representations of what images look like, right? And that's sort of the main innovation of this work. Let's contrast that to finance. Right? In finance, the main kind of predictive problem we're thinking about is predicting returns, predicting asset prices. This is really hard. You can't train a 2-year-old to predict, the stock price, a day or a week or whatever, right? It's very challenging. It's extremely competitive. Many people are trying to do it, and they're competing, and they're, arbing away these edges. The predictions are often very weak, right? So, if you think of a typical stock over the course of a day, might go up or down a couple of %. A fantastic prediction over that kind of time scale might be 1/100th of that. Right, so you're really looking at very, very weak predictions, really just barely above the noise threshold. The predictions you find disappear, right? So you have a great model, year after year after year, it starts working less and less and less, alpha decay. And this is qualitatively a very different problem. It's not that we don't have good representations for how asset prices should behave. It's that it's just a hard problem. Phrased sort of slightly quantitatively, we're in a very, very low signal to noise regime. Right? So this is qualitatively quite different than the problem of object recognition. If we think about doing things like applying deep neural networks, some of those ideas may apply. And in fact, people are applying some of those things, but they won't apply in exactly the same way, and we shouldn't expect necessarily the same kind of breakthroughs. By the way, I think Lasse Petterson has a very nice book and a very nice phrase, efficiently inefficient, right? There are, for these sort of competitive reasons, there are inefficiencies out there, but they're really, really weak, and it will always be that way. That's the natural state of nature, because if they were big, someone would take advantage of it and make money. Right? So that's the first example, image recognition. Let's look at a second example, which I think in some ways is even more impressive, and that's the success of artificial intelligence at strategic games like chess, shogi, Go. Here, in particular, I'm highlighting a piece of work, AlphaZero, that came out of DeepMind, which is a division of Google. They developed, based on deep neural network models, state-of-the-art players for each of these games, better than not only all humans, but also all other machines that existed to date. But that's not the most impressive part about this. The most impressive part about this is it basically did it with no structural knowledge of the game aside from the rules. Right? So they have these neural network architectures that are, quite similar across these three different games. You don't put in any kind of structural knowledge. For example, I know in chess a queen is worth more than a pawn. You don't tell the neural network that, right? You let the neural network discover that in and of itself. And so in some ways, this feels like a form of emergent intelligence. Right? And you get players that are truly state-of-the-art. Now, how does a neural network come to realize that a queen is worth more than a pawn? Well, the thing is you leverage lots and lots of data. By looking at many games, right, you start to see that, hey, if I give up my queen in order to gain a pawn, then that's not a good idea. I end up losing. It's this idea of neural networks combined with reinforcement learning. And so instead of sort of knowledge, putting in the structural knowledge in advance, the knowledge comes out by looking at data. And the nice thing about these particular domains is there is essentially infinite data available, right? And that data comes out through self-play. You have various kinds of computer players, maybe weaker ones, stronger ones. You have them constantly play each other, and essentially you can generate as much data on chess, shogi, Go as you want. And so hence you can leverage, you don't have to be so smart. You can just sort of leverage the data and computation and get the best players that way. What about financial markets? Well, this doesn't work for us, right? Financial markets in many ways, despite the proliferation of data we heard about and gigabytes a day of prices and so on, there is really not that much unique data in terms of independent observations that are relevant, right? In particular, markets are non-stationary over time. Right? We heard that a number of times this morning. If you go sufficiently far back, it's not relevant. If you're building a model for quant equities and you're going to go back more than 10, 15 years, the world was different. Right? Data from 25, 30, 100 years ago is not relevant anymore. You have to look at a relatively narrow window of time to have relevant data, because if you go back too far, the world was different. Investors were different. They had different biases. Market structures were different, so on. Right? So there's a limited amount of look back that you have. You can't necessarily go to other asset classes or other types of products. If you're building a model, like, say, to trade quant equity in the US, you can't trade that on data in Japan, right? It's a different market. Again, different investors, different market structure, and so on. Those predictions may or may not carry over. And the problem gets worse the longer your trade horizon. Right? If you are looking over the course of a day, at least you get one observation per day for security. Right? If you're now trying to make predictions over the time scale of a year, now you only have one observation per year, one truly independent observation, and hence this is a problem. Right? So we don't have the luxury of having infinite data. In fact, we have very little data. That, combined with the fact that the effects we're looking for are just slightly above the noise threshold, means that these ideas, this idea that, hey, we can just sort of build this neural network architecture and throw a bunch of data at it and just get the best investor that ever lived. That's not reality. That's not going to happen. We're not going to see that singularity, right? We can't rely on data alone. There's a lot of insight that goes into this, and that's in terms of opposing structure that comes from the portfolio managers and so on, in terms of how this data is viewed and combined in order to sort of generate models that work well. Right, so we shouldn't expect things like necessarily the revolutions in game playing and object recognition. What's the reality? Well, the reality is this is a little bit of a mature industry, right? At least the mathematical underpinnings for quantitative investing have been around for 50 plus years. Practitioners have been doing it in earnest at least for 30 years. The people who are most successful at it now typically were also doing it 10 years ago, 20 years ago, so on. We're not going to see this singularity where something new and radical and different appears from crazy ideas from deep learning or whatever. Instead, what you see is really careful engineering, incremental improvements over time. People are applying these machine learning ideas, but it's in a much more careful and incremental kind of way. Right? So what I'd like to do with the rest of my time today is to explore that and to try and understand what are the frontiers and what are the challenges and the directions in terms of how people right now on the ground are applying these models. Okay, so just a high-level overview. Many of you may be familiar with this type of thing, but a typical way to sort of think about a quantitative trading, just to sort of make the problem a little bit simpler, is to structurally separate it into a few different steps. And so the first step that people often think about is return prediction, right? Again, our goal here is to be an active investor, to buy low, sell high, or sell high, buy low, something like that. And you've got to have a view on what prices in the future are going to be relative to prices now. So that's predicting returns, right? And trying to apply data and models and so forth to get there. Historically, that was thought to be the only important thing. If you had better predictors and you had better predictions, that was sort of the key ingredient. And what you did with those predictions, maybe that was second order. But again, over time, markets are competitive. They become more efficient, and inefficiencies disappear, and so on. And what you do downstream from that return prediction, that becomes more and more important. So what are those downstream steps? Portfolio construction. Right? You have a universe of assets that you're trading. Now you have predictions for what the returns are going to be for each of those assets. You have to construct a portfolio to try and be well positioned if those predictions actually occur, right? And balance out things like risk and transaction costs and so on. So you take your predictions, you construct a portfolio. Downstream of that, you have to actually implement it. In other words, you have to sort of achieve that portfolio, and that's the area of trade execution. Then historically, maybe 10, 15, 20 years ago, this was done by humans. The computers would actually sort of print out a list of trades, and you had these human kind of execution traders who would, work the phones and whatever and achieve those positions. But as markets have become more electronic, that's sort of been obviated away, and you have other computers doing this, either in an integrated fashion or a separate fashion, right? So return prediction, portfolio construction, trade execution. And one important thing, which we'll come back to momentarily, is there's kind of a bit of a feedback loop where a trade execution feeds back to portfolio construction through the idea of an interface around transaction costs, price impact, something like that. The idea being, the ideal portfolio you'd like to construct, of course it depends on where you think the prices are going to go, but it also depends on how much it's going to cost to implement that portfolio. Right, and that's something that's often challenging to estimate. It's often something that is time varying and non-stationary and so on. So there has to be a feedback layer where, as you execute trades, you sort of get feedback on how much is it costing me, so to refine the ability to effectively construct a portfolio. So I'm going to dive into each of these in a little bit of detail. Let's start with return prediction. Right, academics often like to say that the markets are efficient. It should be impossible to predict returns. The best prediction of the future price is the current price. We all know that, on the margin, that's kind of not true. there are inefficiencies, and when we think about what are the sources of those inefficiencies and data, there's many. Here's a list. Right, you might think of making predictions based on inefficiencies or data around prices, things like let's say microstructure effects, things like the time series types of effects, momentum or reversals. Traditional stat arb was built around sort of cross-sectional effects. If one stock goes up, correlated stocks should go up. Right, so this kind of technical data, the idea of using prices and trades and so on, that has a very rich history in quantitative investing. More recently, people have gone to all other kinds of data, right? Analyst ratings, fundamental data, news, alternative data. There's an entire industry around this with which I'm sure you're all familiar because of the amount of advertising and press it gets. Right, but the point is there's lots of data to potentially use, again, relatively well known. All things being equal, though, there's been a general shift to moving away from price data to other sources of data because everybody has price data, and the inefficiencies that one can glean from price data are smaller. Right, so a general shift to novel data. How about things in terms of the models and algorithms? Here's, probably you can't sort of see this so well. Here's an enormous taxonomy of machine learning algorithms. People do everything, all of the above. Probably historically and even currently, the #1 most important thing is linear regression. Right, but again, as markets get more efficient, as you try to sort of wring out these signals, which are very difficult to find, there's been a general shift to more complex black box models. Right. So what do I mean by that? One really nice thing about linear regression, aside from the fact that it's workhorse kind of predictive model, is in addition to just giving you predictions, it gives you some structural insight. Right, it gives you some insight into what are the variables that are important. You get things like p-values and t-stats and confidence intervals and so on and so forth. You may believe in that stuff or not, right? But it's there. Right, there's some theory that supports it, and at some level, beyond just giving you a prediction, it's giving you some structural insight into what's going on. Right, the more broader shift as we go to things like neural networks or decision trees or ensemble methods or so on, you start losing that. Right, you start losing any kind of interpretability, any kind of sense of what are the structural drivers, and it becomes more about just predicting the price, and your metric is more just what's my RMSE out of sample. Right, so in some sense, at least from the point of view of the end user, I mean, we care about accurately predicting prices, right? The returns are what are going to make us money. So this is the most important thing. On another, from another sense, we lose something there. But there has been a shift to using these kind of more complex, what I'll call black box methods. Now, that said, I still bet that linear regression is the most commonly used method. I think firms compete on both these fronts, right? If you have unique data, or if you have unique insights in terms of what features to select, you probably don't need anything more than linear regression because it's obvious how to construct a prediction out of that. Right? On the other hand, if you're just going to use price data, which is sort of the thing everybody is looking at is completely arbed away, well, now you're going to need potentially more complex methods. So I think firms compete on both those directions, and it's not always necessarily just about one or the other. Right, so again, probably all of you have heard of many of these algorithms, and all of you have heard of the industry of alternative data and so on. I think there's a number of maybe more subtle issues that arise when you actually try to do this. And these are what I'll call the challenges, right? First and most important thing, the predictions are very weak, right? And in particular, they may not exceed transaction costs, right? You may build a model, I don't know, you build a model based on order book imbalance, right? It'll work, it'll have predictive value, in terms of what the future price evolution will be. But I don't know, you might get a prediction that the price is going to go up half a basis point and the bid-offer spread is 2 basis points, right? You can't make money off that, right? So in order to sort of actually be able to make money, you have to build a number of these independent types of models and combine them. If I have 5 models and they're each predicting half a basis point up and they're independent, and I trade when all of them are firing simultaneously, now I'm going to exceed transaction costs, right? So the challenge isn't to just sort of build one prediction, because your individual models might be very weak. And here by a model, I mean maybe a set of features paired with a machine learning methodology. Each of these models you build, or alphas, may be very weak. But once you start combining them, now you're in business. Right, so when you look at what people actually do, oftentimes you have at least tens, if not hundreds, or even more potentially distinct predictive models that are being combined to form one aggregate prediction, so that you can actually exceed the transaction costs and make money. Right, so the number of challenges here. Number one, how do you do it? How do you take these distinct predictions that are coming from different types of data, different algorithms, and you synthesize them into a composite view, so-called alpha mixing problem, right? Number two, when you're doing this research, when you're managing the, this type of alpha research, how do you manage correlation? If you've built 100 different predictive models already, and you have a researcher and he's out building the 101st with some new data set and some new algorithm and whatever, guess what? It's going to be highly correlated to the 100 things you've done already, right? Because at some level, a lot of these models are picking up the same underlying inefficiencies in the market. Right? And so if you build something that's already correlated to what you already have, you've essentially wasted your time. It's useless. Right? So a challenge is, how do you manage that research in order to sort of extract alphas that are actually independent, that are not correlated? Similarly, we're in this regime, I've already argued, where you have very low SNR and you have limited amounts of data. You're very susceptible to overfitting. Right? Even if you try to do, in sample and out of sample and so on, you go out of sample enough, you're going to overfit. Right? You're going to find something that works, you're going to turn it on in production, and it's going to lose money. Right? So the challenges, in terms of state-of-the-art quantitative investing are issues like this. Let me talk a little bit about portfolio construction. Right? So the traditional approach, dating back to Markowitz and his Nobel Prize, is the idea of thinking of portfolio optimization in a single period framework. Right? Let me walk through what this is about. The idea is to pick a target time horizon. Maybe if you're doing something like, let's say, equity stat arb or something like that, you're going to go out like, I don't know, 10 days, right? 2 weeks, right? You're going to look out 2 weeks, and you're going to have predictions for what the returns of your universe of assets is going to be out for those 2 weeks. You're going to have a risk model. Right, maybe a model for transaction costs, maybe things like concentration limits and other types of constraints, leverage constraints, and so on. You're going to put that into an optimization problem, and you're going to solve to find the portfolio that maximizes your risk-adjusted return, subtracting transaction costs, obeying constraints, and so on, at the time horizon that you looked at. Right? Why do people like this? Because it's very flexible and it's very scalable. Flexible in the sense that it can accommodate all kinds of risk models and transaction cost models and so on. Scalable in the sense that you can solve this problem, in universes of tens of thousands of assets. All works very well. And the idea is, maybe you wake up in the morning and you have your 10-day horizon. You do this once. You come up with a portfolio, and periodically you replan. Maybe, the next morning, probably these days more often, every, 15 minutes, sort of something like that. In engineering, we call this model predictive control, right? But the truth is this falls short. The true problem isn't a single period problem. It's not that you're just looking at a fixed horizon. The true problem is we're living in what's effectively continuous time, right? I can make a decision now, but I can revisit it in a minute. And this isn't capturing that. And there's a number of ways this model falls short, but I'm going to sort of highlight one particular defect, which is, how do you pick that time horizon? Where did this 2 weeks come from? Why am I optimizing looking out 2 weeks? Right? So let's sort of think about that. If you think about where that time horizon should come from, it should line up with two things. Right? One is it should line up with your predictive models, your return predictions. If you're making return predictions out 6 months, but you're only sort of planning out 2 weeks, you're not going to earn that full return. Right? Similarly, if your predictions are shorter, if I'm predicting out a day, but I'm planning out 2 weeks, I'm holding assets and taking risk that is unnecessary. Right? So ideally, you'd like to align your portfolio optimization problem with the time horizon of your predictions. Right? Second thing is, you'd also like to align it with the time horizon of your assets, phrased differently, with your trading hold times. right? If I'm making a plan so that, I'm planning out 1 month in advance, well, whatever comes out of this endogenously, I should have a typical hold time of 1 month. Right? Again, otherwise, my plan is not going to be aligned with the actual trading, and I'm not going to achieve the results that I want. Right? So, a little bit of a chicken and egg problem. The portfolio optimization is generating the trades, and what you'd like is somehow those trades dynamically to be consistent with your assumptions in the portfolio optimization problem. So two types of disparate things, but actually the bigger problem than all of this is that both of these vary over multiple orders of magnitude, even within the same asset class. Right? So again, let's take quantitative equities. Let's think about predictive time horizons. I gave a bunch of different types of inefficiencies. You may have a microstructure alpha order book imbalance, right? If you observe that the order book is imbalanced, right, that prediction will realize itself on the order of seconds. Right? But, that can't be your only prediction. Again, you have to have many of these things, and you have to combine them. If you have a prediction based on earnings, you think, whoever it is, Apple is going to miss its earnings. When is that going to be realized? It's going to be realized when the earnings occur, right? So that might be weeks or months. Right? So if you look at, we argued we need many of these predictors, and they naturally vary over multiple orders of magnitude. What should I use for my planning horizon? It's not clear. Right? And even more subtly than that, the trading hold times, again, within a single asset class will vary dramatically, because your hold times, really, if you think about it, they should be driven by the liquidity of the assets. And again, let's pick a relatively narrow asset class, U.S. equities. Right? If you're trading within U.S. equities, an asset that is very liquid, let's say at the limit, let's say it's extremely liquid, it's free to trade, no transaction costs, then your hold time should be very, very short. Basically, if you see an iota of positive expectation, you should buy, and if you see an iota of negative expectation, you should sell. Right? So you should be moving in and out constantly. On the other hand, if you go to the other extreme and you think of an asset that's illiquid, right, you're going to have to wait a while to have a large signal before you enter into the trade. And similarly to exit from the trade, your hold times are going to be long. Right? And so, if you calibrate transaction cost models and compare them to predictions and so on. And again, look at a relatively, I would say homogeneous universe, U.S. equities trading, let's say the top 3,000 names. If you're trading Apple, which is a very liquid name, you should be turning that over 2 to 3 orders of magnitude faster than, let's say, the names in the range 2,000 to 3,000 in terms of liquidity. Right, so again, a single asset class, it's not optimal to have just one hold time. It needs to vary because the liquidity varies, and your predictions vary in terms of their time horizon. Right? This is naturally a multi-period problem, and state of the art, you've got to consider it as a multi-period problem. And in particular, 2 kinds of implications of that. The first is when we're making return predictions, we care not only about what's the prediction, but how is it realized? In other words, what's the trajectory? Right? I'm not going to look at only okay, it's going to eventually go up 10 basis points, but I'd like to know how much of that is going to occur in the next hour, the next day, the next 10 days, something like that. Some kind of view of the trajectory. Right? Because I want to be able to accommodate predictive models that operate at all of those different time horizons. Right? Similarly for the asset classes. Again, if I'm trading Apple, my predictions at the very front of that forecast term structure, if you will, those are the ones that are relevant. But for the less liquid names, I need to be thinking out, maybe weeks, maybe months even. Right? So you need to make predictions of trajectories, and you need to sort of fundamentally consider multi-period formulations based around dynamic programming. Right? Now these are very challenging. Right? It's very difficult to come up with sort of the truly optimal policy. There's whole areas, things like approximate dynamic programming and so on. But roughly the state of the art is to sort of identify maybe a parameterized class of policies with some number of knobs that you can turn, and then to try and optimize that, right? So you could optimize that, back testing, doing, grid searches over this parametric space. If you're more sophisticated, you might explore ideas like reinforcement learning to basically tune within this tractable class of policies what is the best policy that maps, trajectories of returns across your universe to a portfolio. So that's portfolio construction. How about execution and trading? I'm going to focus on the estimation of trading costs. This is very important, right? Trading costs, it's obviously not free to trade, right? Having a better estimates of trading costs allows more efficient monetization, also allows you to trade more aggressively, right? In particular, as your participation rate goes up, as you're trading more aggressively, trading cost estimates are noisier typically, right? So we'd like that to be better. For a large investor, the number one source of trading costs is price impact, market impact, right? As you, let's say, buy and buy and buy, you're going to drive the price up. And the challenge here is this is not a price that you see like on a menu. It's an implicit cost. It's not obvious, right? You're just noticing you're buying. The price is going up. Sometimes it'll go down, right? Why? Because again, there's a lot of noise, right? The trading costs that you're paying are masked by the noise in the market. Right, so the way you measure trading costs is you look at not just if you give me one trade, it's very hard to say what the trading costs are. I have to assemble a database of many of these, right? Moreover, what makes things even harder is I'd like to establish causality. I'd like to establish that, for example, the average effect of the price move due to my trade, right? Cause effect. I traded, the price went up. I bought, the price went up, right? Very often, this is masked by confounding factors, right? So let me give you an example. Suppose you're trading on a momentum signal. You have a momentum signal, says the stock price is going to go up. You buy, you observe that it goes up. You average this over many trades, you get a price impact model, right? Now, what may be happening actually is that there's lots of other people who know about that momentum signal. It may be the case that had you not traded, the price would have gone up anyway. Right? Because those other people would have traded and they would have driven up the price, right? So what you may be doing in that kind of situation is you may be overestimating your own price impact, right? And so, again, from these types of, because of the market noise, because of confounding factors, very difficult to establish causality, right? You try to, take that price impact model and, you use it to trade some other signal, it doesn't work, right? It's inaccurate, right? So again, a very active area of research in practice more than in academia, but accurate everywhere. But I think, when we think about causality, what is the state of the art in terms of understanding cause-effect relationships? When the stakes are extremely high, let's say in medicine, what do? You do randomized trials. You do A/B testing, right? And to some extent, to understand causality in terms of short-term impact of trading on price, you have to do some flavor of randomized experimentation. Maybe not quite, as extreme as A/B testing, but introducing some randomness in your trading in order to be able to separate the effects of your trading from the effects of maybe confounding factors, which don't apply when things are randomized. And one very interesting thing, tidbit that mentioned in this article and that I've heard anecdotally is when we think of one of the most successful, if not the most successful quantitative investor ever is Renaissance Technologies, right? There's a widespread view that maybe they have great predictive models and so on, maybe better than other people, but one of their big advantages is thought to be that they have a better understanding of transaction costs than others, and they're able to more aggressively trade and monetize their signals than other people can. Right, so this is a very interesting and challenging area. Okay, so I'm going to use a little bit more time to talk about some other trends and where I think things might be going forward. One thing I haven't mentioned so far is the role of computation. I think maybe already and certainly going forward, large-scale computation is going to be very important. Right? It is certainly important in some of these other examples in artificial intelligence and machine learning that I've talked about. In many of these cases, again, we don't have a lot of structural insight. With these deep neural networks playing, Go or whatever, right? We don't know what's going on. We don't know what's going on in the game of Go, but we sort of get those insights through experimentation, through simulation. Right? In the financial context, increasingly, again, as the models get more complex, it's not clear what's going on from the perspective of an economist, right? But you're also going to get insights through experimentation, through backtesting, and these types of things. This requires a computation. You may be working with large data sets. Particular types of algorithms, gradient-based algorithms, seem to be especially slow. This is expensive and oftentimes needs specialized hardware. So to give you a concrete example, I mentioned the Google DeepMind work on Go. not the Alpha Zero, but an earlier version, AlphaGo Zero it was called. People have estimated that in order to replicate the computational results that they published in that paper that they did with Google's infrastructure, if you went out and rented that infrastructure from Google, which they will gladly rent to you, it would have cost $25 to $35 million. Right, this is for one paper, and playing Go, something which has intellectually interesting, but maybe no direct economic value. Right, and thinking more broadly, looking at a company like Google, right? They internally, they're probably one of the biggest consumers of computation globally, if not the biggest, right? And have one of the largest computational infrastructures, data centers everywhere around the globe. Right, I couldn't even estimate how many CPUs. If you were to look at what they do with their computation, they're not open about this. There's some degree anecdotal, but what I've heard is that the #1 use of computation internal to Google is not indexing the web, is not serving you web pages or getting you your Gmail or whatever. It is training machine learning models. #1 use of computation inside Google, and I think that is going to spread. Right? Within finance, within quantitative investing, large-scale computing resources are going to be a significant cost and potentially an advantage of one flavor over another. And just to share another anecdote, I heard recently that the way one large quantitative trader is organized is, they have different quants doing alpha research. And so let's say you have a PhD level quant doing alpha research. Each alpha researcher is allocated a budget of 10,000 CPUs. Right? Just to put some perspective on that, 10,000 CPUs, ballpark would cost about $1 million a year. Right? So maybe they're not using that all the time. The utilization is less. Maybe average that out a little bit, so on and so forth. But we're getting into a world where we're going to be spending lots of money and energy and resources on computation. Okay, I'm gonna wrap up quickly. Another kind of phenomena that I think we're starting to see in this area is that there are increasing returns to scale in terms of being a quantitative investment manager, right? We've already just talked about the costs for technical and computational infrastructure. These represent large fixed costs, right? And so they're going to benefit the largest players. Right? The idea that you have these many weak models and you need to sum them up in order to exceed transaction costs, that also creates an increasing returns to scale phenomena, right? In particular, if you have 100 models already and you're comfortably often exceeding transaction costs, if I were to add one more model, probably that will be pure profit, right? Or certainly more so than if I have nothing, right? So there's increasing returns to scale in terms of the quantitative research. And again, as I argued, it's helpful to develop things in a coordinated way, right, in order to avoid correlation between different alphas and in order to be able to mix alphas in a meaningful way. So I think this has a number of implications for how the industry is going to evolve. First of all, you're going to get fewer larger firms versus small shops, right? Increasing returns to scale creates oligopolies, so that's what's going to happen. Right, the industry is going to be dominated by very large firms. Number two, if you look at the way large quantitative firms are structured, there are typically two models. There's a model where, like, let's say within an asset class, let's say quant equities, right? You have a centralized trading strategy where a whole bunch of people doing alpha research, a bunch of people doing alpha mixing, some people doing portfolio optimization, and so on. But it's all towards one strategy. Right, so that's the model at places like Renaissance and Two Sigma and so on. On the other hand, there are other types of models, places like Cubist or Millennium, other types of firms where it's more about having independent PMs with maybe teams of like 2 to 5. My prediction is that the centralized strategies are going to win. Again, you have these increasing returns to scale. It works much better if people are coordinating rather than if you have independent PMs working in the same asset class doing their own thing. Finally, and I think I'm pleasantly surprised to hear this from multiple practitioners in the session earlier. I think the boundaries between medium frequency and long frequency quantitative trading and high frequency trading are going to disappear. Right? In other words, you're going to have these, stat arb guys, medium frequency guys, whatever, moving down to shorter time horizons, adding signals, like microstructure signals and so on. At the same time, you'd have people who are traditionally doing HFT who come from a very different lineage. You're going to have them moving out. holding positions for longer, incorporating signals that are realized over longer periods of time, and so on. And again, the idea is you have these increasing returns to scale. You need to use as much information as you can. Some of the phenomena are going to be short-term. Some of the phenomena are going to be longer-term. And those people who can combine those effectively are going to be the ones who have the most advantage. I will stop there.